Welcome back, everyone. Before I begin, let me ask a few questions. How does Google's search algorithm rank web pages? How does a GPS system efficiently navigate you through a bustling city? Or how does a logistics company optimize the supply chain operations? In our previous video, we explored system of equations. Today, we're taking it up a notch and diving into the powerful technique known as Gaussian elimination. This method allows us to systematically solve systems of equations by transforming them into an easier form. As always, we'll begin as progression from easy to hard examples. Before we begin, let's understand the concept behind Gaussian elimination. It's a systematic method that involves performing elementary row operations to transform a system of equations into row echelon form or reduced row echelon form. This process simplifies the system, making it easier to solve. Now, let's put this technique into our action with our first example. Consider the following system of equations. The pencil went out. Whoops. Okay, we're in. We have x plus y equals 5. And in equation 2, we have 2x minus y equals 1. To apply Gaussian elimination, we'll create an augmented matrix by combining the coefficients and constants of the equations. Our augmented matrix looks like this. Now, let's perform elementary row operations to transform this matrix into row echelon form. We'll start by using the first row to eliminate the coefficient below it. We'll multiply equation 2 by -2, and then we're going to add it to equation 1. As a result, we get this new augmented matrix. Oh, there's an error. This should be -9. Great. The coefficient below the leading 1 in the first row is eliminated. Now we'll simplify it further by dividing the second row by -3 to obtain a leading 1, which can be denoted as R2 divided by -3. As a result, we get 1, 1, 5, then 0, 1, 3. Finally, we'll use the second row to eliminate the coefficient above it. Let's multiply equation 2 or row 2 by -1. And then add it to row 1. As a result, our augmented matrix should look something like this. And there you have it. Our augmented matrix is now in row echelon form. We can easily read this solution from it. X is equal to 2 and y is equal to 3. Okay, now let's move on to a medium example. First equation, we have 3x plus 2y minus z equals 1. And second equation, we have x minus y plus z equals 2. And 2x plus 3y minus 2z equals -1. First thing first, we are going to convert this system of equations into an augmented matrix. So we have 3, 2, -1, 1, 1, -1, 1, 2, 2, 3, -2, -1. It is vital to draw a vertical line separating the vertical line representing the equal symbol. And now we are going to implement a series of matrix operations that will yield a matrix presented in row echelon form. So the first thing we're going to do is we are going to grab row 2 and subtract it by row 1 divided by 3. We will then move that to row 2. As a result, we get 3, 2, -1 and 1, 0, -5/3, 4/3, and 5/3. Then in row 3 we'll have 2, 3, -2, and -1. And I'm going to try to draw a perfect line right over there. And then next up we'll do another row operation where we'll grab row 3, subtract it by 2/3 times row 1, and move that to row 3. So therefore row 1 and row 2 should be the same. And row 3 ends up being 0, 5/3, -4/3, and -5/3. Right on. At this point, you guys are going to see a pattern. We will then grab row 3 again and subtract it by -1 times row 2 and move this difference to row 3. Sorry, I meant to say row 3 subtracted by row 2 and move it to row 3. As a result, we get one row full of zeros, and we have -5/3, 4/3, and 5/3. Yep. Yeah, rows 1 and 2 should be the same. You'll see over here that we have a row of zeros, and 0 right here underneath leading coefficient. This is row echelon form where you have a row of zeros and a column of zeros with one leading coefficient, as demonstrated right here. As a result, we will convert this augmented matrix back into a system of equations where we have 3x plus 2y minus z equals 1, and we have -5/3 y plus 4/3 z equals 5/3. Let me make this more readable for the audience. Oh, that's supposed to be a z. Okay. Our first step is we're going to grab row, or our second equation, and we are going to solve for y. Yep, we're going to solve for y. So, to do that, we'll subtract 4/3 z on both sides. And we get 5/3 minus 4/3 times z. And this, don't forget to include your variables. And then we're going to multiply by the reciprocal of -5/3. As a result, y should be -1 plus 4/5 times z. That was our first step. Now we're going to grab our first equation and we are going to solve for x. To do that, let's write down our equation again. 3x plus 2y minus z equals 1. Over here we're going to add z and subtract 2y. As a result, we get 3x equals 1 minus 2y plus z. Now, we've already deduced the second identity of y, so we're going to grab what we got y as, and we're going to move it into the first equation via substitution. So we have 1 minus 2 times negative 1 plus 4/3 times z plus z. And then we are going to solve accordingly. Let's distribute the negative 2 and then add like terms. As a result, you get 3 minus 3/5 times z, all of which is equal to 3x. We can then divide both sides by 3 to isolate x, and we get 1 minus 1/5 times z. So over here we have x equal to 1 minus negative 1/5 times z, and we also have y. Okay, so after implementing Gaussian elimination, we have our three solutions. Y is equal to negative 1 plus 4/5 times z, x is equal to 1 minus 1/5 times z, and for our z variable, we have, well, just z, because in this process, there's already a row of zeros, and if we were to solve for z in this matrix, it'd just be z. And now, we're not actually done yet. We still gotta present this as an actual, or we still gotta present this as a general solution. So we'll define the matrix as A, and because Gaussian elimination is finding the inverse of a given matrix, it's a to negative first power, which is equal to x, y, z, and as a result, a negative 1 is equal to 1 minus 1/5 times z, negative 1 plus 4/5 times z, and we get z in the bottom. And there you have it. That is our solution for this given matrix. Okay, everyone, it's time to buckle up. This is probably gonna be one of the crazier matrices you're gonna see. So let's start off with a system of equations. We have, again with the stylus, Jesus. Okay. We have 2x plus y minus z equals 3. The second equation is 3x minus y plus 2z equals negative 1. And then the third equation is x plus 2y plus 3z equals 4. First things first, let's make this an augmented matrix. We have 2, 1, negative 1, 3, 3, negative 1, 2, negative 1, 1, 2, 3, and 4. Right on. So we're going to implement the following matrix operations. So let's grab row 2 and subtract it by 3/2 times row 1, we're going to move that to row 2. So evidently row 1 and 3 should be the same, and there should be change in row 2. So we have 0, negative 5 halves, and then, it's 7 halves, and a negative 11 halves. 1, 2, 3, 4 in row 3, 2, 1, negative 1, and 3 in row 1. Next up, we are going to observe, and then I think the best move is to grab row 3 subtracted by 1 halves row 1, and then move that change to row 3. So therefore, row 1 should be as is. Row 2 is 0, negative 5 halves, 7 halves, and negative 11 halves. And row 3 becomes 0, 3 halves, 7 halves, and 5 halves. Next up, let's see here. You guys can already see it's about to be turned to row echelon form, and I think this is going to be the final move. Let's grab row 3 and subtract it by negative 3 halves times row 2, and move the change to row 3. So we get 0, 0, 28 fifths, and negative 4 fifths. Is that right? Yeah, that's right. And row 1 and 2 will stay as is. Yeah. Yes, they will. So while I'm writing down row 1, row 2, I'm going to ask you guys what's our next move. And I'll give you a hint, it's very similar to what we did before. Okay. Look at the bundle of zeros. It's an indicator that we're in row echelon form, and this is going to allow us to grab this augmented matrix and convert it back into a system of equations and solve our individual variables. So let's do that. So converting everything back, we get 2x plus y minus z equals 3, negative 3 halves y plus 7 halves z equals negative 11 halves. And we have 28 over 5z equals negative 4 fifths. So, which of the three variables are we going to solve first? Personally, I'll go with the third one, or the third equation. So 28 over 5 times z equals negative 4 fifths. We can multiply by the reciprocal of 28 fifths, and we get z is equal to negative 1/7. Okay, we have one solution, and I think we're going to have to work our way up in the system of equations. So we'll grab equation 2, negative 3 halves times y plus 7 halves times z equals negative 11 halves. From here, we can substitute z for negative 1/7, and we end up getting negative 3 halves times y, 7 halves times negative 1/7, that's negative 1 half equals negative 11 over 2. And then we'll add 1 half. Let's not do 2 steps from 1. Negative 3 halves y equals, let's see here. I'm having a little brain fart at the moment. That should be negative 5. If we multiply by the opposite reciprocal, we should have y is equal to 2. But if y is equals to 2, that means, Alright everyone, let's see where I messed up. So, oh, wait a second. 5/2. Something's wrong, bro. Oh, see? This is supposed to be negative 5/2. There we go. Sheesh. Oh, okay. Thankfully, it was an easy mistake to point out. So, okay. Yeah, I knew there was something wrong where if I plug in y into this step, it's not going to give me negative 5. So, let's see here. Okay, negative 5 multiplied by the reciprocal, and we should get 2. Yes, right on. Okay, we got the value of y. Now, I said we were going to work our way up, and I actually meant it. So, first equation was this one right here. We're going to bring that down. So we have our x and we have our y and z variables. So let's just solve for x. We know that y was negative 1/7 and z was 2. Or add like terms and then divide by 2. And as a result, we get 2x equals 6/7. Divide by 2 on both sides, and we get 3/7. Now, as a result, the inverse of the given matrix is equal to x, y, z, which is equivalent to 3/7, negative 1/7, and 2. Alright folks, that was it's on the harder side of Gaussian elimination, and it looks like we have mastered the process of doing so. By transforming augmented matrices into row echelon or reduced row echelon form, we can easily obtain solutions. Please keep practicing this method, and soon you'll achieve a sense of mastery. Don't forget to like, share, and subscribe for more math tutorials. Until next time, happy problem solving.